In this video, we're going to talk about probability. And so we're going to first start by defining some terms related to probability, and then we'll get to how we can calculate probability. Probability can be defined, just one definition, as the way that we quantify uncertainty, which is due to randomness, right? And so if you have something that's going on and you don't know the outcome is uncertain, it can go one of several ways. Then that is considered a random phenomenon. And basically, probability is a way to quantify that uncertainty. And this is basically based off of what we call a random experiment. A random experiment is any action or observable experiment where the outcome is random. Now, I know we're using the word experiment here, but things as simple as flipping a coin is an example of a random experiment. Before you actually flip that coin, you don't know the outcome of whether that coin is going to be land on heads or tails, right? And so that's considered a random experiment. Playing the lottery, before you select your numbers for the lottery, you do not know what the actual numbers are going to be that are going to be selected from that lottery. And so that's another example of a random experiment. And we actually see a lot of random experiments every day, right? So, for instance, on your way to work or school, you pass a bunch of stoplights and you don't know whether it's truly going to be a red or a green light or a yellow light, right? Now, we can kind of anticipate some things, but we don't know when it's going to turn red or yellow, or we don't know how many stoplights we're going to actually be stopped at on red on our way to work through the stoplights that we encounter, right? So all of these can be thought of as like random experiments. Another definition of probability, the probability of a particular outcome, that's a particular outcome in that experiment, and it's like landing on heads or the numbers 535 being your lottery numbers. It is basically the proportion of times the outcome would occur in a long run of observations. And so if you wanted to write this using some sort of a formula, I can say that the probability can be defined as the number of times a desired outcome occurs. And I'm going to divide that by, since I can type faster than I can write, and we're going to divide that by the number of possible outcomes, right? And that's kind of like the total number of possible outcomes. And so when I look at those things, that proportion, right? I do the part over the whole, the total, and that will give me a number that I can use to get probability of a particular outcome. And so let's look at this example where we use this. It says you randomly sample 10 freshmen at USC, right? So from the whole population of freshmen at USC, you randomly select 10 freshmen, right? And you find out that none of them actually eat at the Russell House. Does this mean that the probability that a USC freshman will eat at the Russell House equals zero? Our answer to that question would be no. All right. Now, in your experiment, the probability that you select those individuals and you get 0 out of 10 that eat at the Russell House or that don't eat at the Russell House, that's that probability. But we can't say that about the greater population. So we're going to say no because we don't have a long run of observations to base the probability on. We only have 10 observations. And so we can't make those big, broad statements that, oh, that's the probability that a student at USC eats that will eat at the Russell House will be 0 out of 10. We can't do that because the probability actually requires a long run of observations. All right. One of the reasons for this is the law of large numbers. It says as the number of trials increases, that's every time we run a random experiment, we call that a trial. And so As the number of trials increases, the proportion of occurrences of any given outcome approaches the probability in the long run. And so, based off the law of large numbers, if I increased my random sample from 10 freshmen to maybe 100 freshmen, or to 200 freshmen, or to 500 freshmen, I'm going to get closer and closer to the true probability, which represents the probability in the long run. All right. So we want to you do our experiment so many times so that we can get close to the true probability, which is that probability based off of a long run of observations. The last thing we'll talk about here is independent trials. Trials of independent phenomena are independent if the outcome of one trial is not impacted or affected. I always get effect and affect mixed up, or impacted or affected by the outcome of another trial. All right. And so an example of this, when two trials or trials are independent, let's suppose that we have a bag of 5 red marbles and 5 blue marbles, right? And what we're going to do with those, our experiment has 2 trials. And what we're going to do is we're going to select 2 marbles, all right? Well, there's a way to select those marbles so that our trials are independent, and there's a way to select those 2 trials so that our selections or our experiment is independent. Our trials are independent, all right? So let's talk about when they are dependent, all right? Dependent trials. Dependent means, okay, when I select my first, I'm going to do this in order, right? Dependent means the trials impact each other. The probability of one outcome is affected by another outcome, right? And so what I'll do first is I'll select one marble, okay? I'll select another marble without replacing the first marble back. Okay. Well, since there were 10 marbles in the bag at first, and I selected one of those marbles, right? The probability that that is a blue or a red marble, either or, it doesn't matter. Let's go at red. The probability that it's a red marble is 5 out of 10, right? Because there's 5 red marbles in there and there's 10 in total. Well, if I don't put that marble back in, now there's 9 marbles left. And so the probability of selecting a red marble now is going to be out of 9 instead of out of the 10, right? And so the probability changed from one trial to the next. That means that the trials are dependent, all right? For trials to be independent, then what I'll have to do is first I'll select one marble, and then I'll put it back in the bag. And then what I'll do is I'll select the second marble. So when I do this, I select my marble, my first marble from my first trial, I put it back in the bag. When I put it back, there's still 10 marbles left, right? And then I select my second one. The probability is going to be based off of basically the same thing as the first trial, as a probability from my first trial. And so those two, selecting those in that manner will create independent trials. When I select and I put it back in, this is called, in statistics, this is called sampling, sampling with replacement. That means I'm going to sample it and I'm going to place it back in the bag. Sample it, place it back in the bag. So I'm sampling with replacement. That creates independent trials. All right. When I select one and I keep it out, that's sampling without replacement. And that creates dependent trials. All right. So this is basically some vocabulary that's related to probability. It's all about quantifying that randomness, that uncertainty due to randomness. And it can be thought of as the long run probability of getting your desired outcome, the proportion of times that desired outcome is going to occur in the long run, right? And in the long run, it's almost like going to infinity, right? Like, what is the proportion of times out of infinity that I will land on heads? That's the probability of landing on heads. Of course, in real life, we can't do an experiment in an infinite number of times, and so in real life, we can kind of get some experimental probabilities that are kind of theoretical. All right, and that's what we're going to talk about here in the next section. All right. And so these next two sections are about finding probabilities and conditional probabilities. And so we're going to define a bunch of terms here. For instance, a sample space. A sample space is the set of all possible outcomes in an experiment. All right. And so let's say our experiment is rolling a dice. So my sample space, and we usually use the letter capital S to represent your sample space. If I roll a six-sided, I'm going to say a six-sided dice, and they're multiple-sided. You can go up to 12. There are dice that are many-sided, right? But a six-sided dice, my sample space, I can land on a 1, a 2, a 3, a 4, a 5, or a 6. And so the possible outcomes from doing an experiment of rolling one dice is I get one of the numbers from 1 to 6. An event is a subset of the sample space. All right, an event corresponds to a particular outcome or a group of particular outcomes that you're interested in, right? And so, what if I wanted my event to be rolling a number that's odd, right? Or rolling an odd number. Then my event, usually we'll use a capital letter like A, will consist of the numbers or values in my sample space that are odd. So I will have the set 1, 3, and 5. All right. So if we want to know the probability of the event, all right, if all outcomes are equally likely, right? And this is what we assume a lot, that our things are equally likely, right? Um, that means things are fair. I don't have a higher probability of rolling a 4 compared to having a higher rolling a 2 or a 1, right? That's what equally likely means, that everything has the same probability of occurring, right? When that is the case, the probability of the event is given by, all right, this P of A. This is the probability of event A is, I'm going to say N sub A, N of A over N of S, all right? And what that equals, this is the number of elements in event A. And what we're going to do with that number of elements in event A is we're going to divide it by, and we're going to make this a little longer, the number of elements in the sample space S. All right. So we divide the number of elements in event A by the number of elements in our sample space. And so if we look at that example of rolling a dice and my event A is the rolling an odd number, then in that example, the probability of rolling an odd number would be 1, 2, 3. There are 3 odd numbers or 3 elements in our event, and our sample space has 6 elements. So we get 3 out of 6. Uh-oh. 3 out of 6, which is 1/2. We can write it as a simplified fraction, or we can write it as 0.5. All right, and so that's a probability. There are some things that are always going to be true about probabilities. There will always be numbers that look like this. And more specifically, probabilities cannot be negative. They're always going to be greater than zero. They can't be negative. For any event A, the probability of event A has to be a range in value from 0 to 1. And then the sum of the probability of all possible outcomes of a random experiment has to equal 1. All right. And so these are some rules or properties of probabilities. All right. And so here we have another example. I kind of went over this example here already, but let's do this once again. Suppose you roll a six-sided dice. List the sample space, right? So our sample space is usually given by the variable S. We have a six-sided dice, 1, 2, 3, 4, 5, 6, and there we go. Let event A be the event that you roll a multiple of 3. So event A will be given by, I'm going to list the elements. By the way, when you list numbers or list elements, then you just use these squiggly brackets. I know this one looks weird. And then you just separate the elements by a comma. But multiples of 3 are like counting by 3, like 3 and 6. Those are the only two multiples of 3 that's in that sample space. And so it says, suppose all outcomes are equally likely. Find the probability of event A. That's the probability of rolling a multiple of 3. Well, there's 2 elements here. There's 6 elements there. So the probability is 1/3, which if I write that as a decimal, 0.3 repeating. All right, so that's that example. Let's do another example. Let's say we roll 2 six-sided die. All right. Our sample space, let's do the sample space. Our sample space is going to be much bigger, right? Our sample space is going to look something like that. Now, a sample space, we're going to list the elements, right? What I'm going to do is I'm going to say, okay, well, I can roll a 1 on one of the dice and a 1 on the other dice, right? And so I'm going to say 1, 1. I can do a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6, right? So a 1 on one dice, and then 1, 2, 3, 4, 5, or 6 on the other, right? Then I can roll a 2 on the first dice and a 1 on the second, right? So I get 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6, right? And this is if we can distinguish between the two dice, right? Which we'll assume here. Then I can roll the 3 first, 3 and a 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, right? Then I can do a 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. And we will continue because it's 6 sides, and so we get all combinations of the numbers 1 through 6 paired with each other. And this is tedious, I know. All right, now I put it like it looks like a subtraction or a dash, but these are all the elements in my sample space. And there are 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. So there are 6 times 6 elements in that sample space, all right? And so part B, let's let event A be the event that we roll a sum less than 4, right? Event A is going to be the event that we roll and we get a sum that's less than 4. So I'm going to list all the elements in event A, right? Well, if I roll a 1, 1, that's sums to 2, so that's less than 4. I'm going to do a 1, 2, that's less than 4. And when I get to 1, 3, that's more than 4, right? I can do a 2, 1, that's less than 4. But once I get to 2, 2, that equals 4, right? So all of these are greater. And no other elements in my sample space has this property here. And so that is event A. And so if I wanted to go to part C and find the probability of event A, given that rolling the dice the outcomes are equally likely, then what I'm going to do is going to be the number of times event A occurs, which 1, 2, 3 is the number of elements in event A, divided by the total number of elements, which is in the sample space, which is 36. And so we get 1 over 12. And so that's the probability that we roll a number less than 4, and that's approximately 0.08, and then the 3 is repeating only. All right. And I just realized that you can't fully see all of that, so I am so sorry. But if we look here, there we go. All right. So that is just calculating probability, introducing you to some of the terminology like sample space and things of that nature. And so what we're going to do now is we're going to get to some adjectives that are related to probabilities. And some of these adjectives include things such as complement of an event, right? The complement of event A is denoted A complement, A with a subscript C. And this is a set of all outcomes that's not in A, right? I'm going to draw some diagrams to help us understand this. Our rectangles represent our sample space, and our circles represent events. And so if I look at this complement of an event, when I do the complement of event, I'm going to draw this rectangle. That's a sample space S. If I draw a circle in there, it represents my event. So everything that's within this circle represents event A. Everything within this rectangle represents my entire sample space. So if I want a complement, I want everything that's in my sample space, but that's not within event A. And basically, it's everything on the outside of that circle, but that is within this rectangle. And so that's a complement of an event. Disjoint events, events A and B are disjoint if they do not have any common outcomes, right? And so what I'm going to have here in this scenario is that we're going to have our sample space, which is S, and A and B are two events, but they're disjoint. That means they don't overlap. That means if I have a circle representing event A, I have a circle representing event B, there is no overlap because they don't have any common outcomes, all right? When events A and B are not disjoint, we can calculate things from it. For instance, we can do the intersection of events A and B. The intersection of events A and B consists of outcomes that are in both A and B, right? And so now, instead of them being disjoint, where they don't overlap, now event A and event B do overlap, all right? So this is for events that are not disjoint. Now the intersection, a key word for intersection is the fact that it has to be in both A and B, the word and, all right? And so you have to be in event A and B, you get this little piece here that's the overlap, right? So any events there is in the intersection. And the notation that we use, if we don't use the A and B, we actually use the notation A with the intersect symbol with B, all right? In addition to being able to calculate the intersection, we can calculate the union of two events. The word union is synonymous for us with the word or. The union of events A and B consists of outcomes that are in A or B, or they can be in both A and B, right? And so if I draw my sample space, and let's say that they're not disjoint. We don't have information that they're disjoint, so that means they're in an overlap, right? Well, you can be in event A, which includes all of this stuff, or you can be in event B, right? And it includes this stuff in the middle, right? And so all of this shaded region represents A or B, the union. And with the union, instead of having this symbol that looks like that, we have a symbol that looks like a capital U, but it's actually a union symbol, okay? You can be in one or the other or both, okay? And so with these probability adjectives, we can actually calculate or use probability rules. And so there is a complement rule that we're going to want to know and memorize, right? Remember, we just said the complement of event A is represented by a complement. And so notice that when I use this P, I'm saying what's the probability of a complement, right? And so just as a review, we're going to draw our sample space. We only have A. This is our event A. And so a complement is everything that's outside of A, right? Now notice if I did the probability of A and I added that to the probability of A complement, because A complements everything else in my sample space, remember the probability of the total sum of all possible outcomes equals 1. Well, if I have A and A complement, the probabilities separately add up to 1. And so if I want to know my probability rule, I can use this fact here. And if I subtract probability of A from both sides, I get 1 minus the probability of A. And so that is what my complement rule is. The probability of a complement is 1 minus the probability of A. All right, and I almost made a mistake there. That's probability of A. We also have the additive rule, right? And the additive rule allows us to calculate the probability of a union of two events, right? And so if I want to do that, and this is event A and this is event B. Well, the probability of event A or B, remember, it has to be stuff that's in the probability in the event A, right? So it's going to include probability of A. And it also has to include things that are in event B. So I'm going to add to that the probability of event B. But notice what I did. I added the things that are in the intersection between A and B, which is this part here. These were added twice. And so I put that overlap on there. Well, the union doesn't add that stuff twice. And so what we have to do to make this work is we have to subtract off adding that twice, and that represents the intersection. And so we have to subtract off one of those plus A intersect B. And so the probability of a union of the two events is the probability of A plus the probability of B minus the probability of A intersect B. Now, this is when we have overlap, right? Now, if we didn't have overlap, we can also calculate the probability of that union, all right? Remember, for disjoint events, so if this is my sample space, and this is event A, and it's disjoint with event B, remember your union symbol represents OR, so it's either in this set or it's in that set, right? And so the probability of this is probability of A, and the probability of this is the probability of B. All right. All right, and that is it, right? There is no intersection. The probability of A intersect B is 0. And so what we don't have is we don't have this term right here because there is no overlap, right? And so we don't have to worry about that when the two events are disjoint. Conditional probability, right? Conditional probability involves the probability of an event given that you know the probability of some connected event, all right? Now, let's look at this notation. All right, this is probability of A, and there's a vertical bar, and then B, right? This reads, I'm going to tell you how to read this. This is the probability, all right, and let's make this a little longer, of A, and that vertical bar represents the word given, and then B, right? So A is the probability that we want to know, but B is the probability, is the event that we already know has occurred, all right? That's why it's called conditional probability. We're conditioning on the fact that we know already event B, but we're interested in calculating the probability of event A given that event B has already occurred. And so what we're going to do here is this actually involves a division, all right? And the way this division works is if we already know the probability of that event B has occurred, B is second after that given. So if I were to draw my sample space S, and I will put events A and B in there, I already know that event B, I have information that event B has occurred, right? And so when I calculate this probability of A given B, it's going to involve the probability of B in the denominator. My goal is to look at out of the probability of out of B already occurring, what's the probability of A happening, right? And so I have my same sample space in my numerator, and I'm basically looking out of B, the probability of A occurring, which is only going to focus on this middle part right here. All right. And so the probability of A given B is basically the probability of A and B, because this section here is the intersection, divided by the probability of B occurring, right? So that is what this intersection equals. Now, I could do it the other way around. I can do the probability of B given A. And so in that case, I have A, a knowledge that A has already occurred. So I know how to calculate the probability of A. That's going to go in my denominator. And then I'm going to do the probability of B intersect A. All right. Now notice here, when you have an intersection, it means that both of them are occurring. So the order in which you write them does not matter. So this is going to be written as the probability of A and B divided by the probability of A. That is what that equals. So what this does for us is we've gone over how we can calculate our unions, right? A union B and A union B for this joint. Now, what we can do is we can create a rule that allows us to get A intersect B, and we call this the multiplication rule. It basically stems from these rules here, right? This first rule, and I'm going to give myself some space. Probability of A given B equals the probability of A and B divided by the probability of B, right? That's what we had over here. And so if I want to know what the probability of A and B is, then all I have to do is multiply both sides of this equation by the probability of B. Probability of B. And they cancel on this right-hand side, and I get the probability of A equals the probability of A given B times the probability of B. We can do a same or a similar calculation using this stuff here. The probability, I'm going to come down here a little, of B given A equals the probability of A intersect B over the probability of A. Again, I can multiply both sides by the probability of A. And what I'm going to see here is that the probability of A's cancel on that side, and I'm just left with this. And so I can say that the probability of A given B is the probability of B given A times the probability of A. This is our multiplication rule, which allows us to get the probability of intersections. But we need conditional probability. We are going to skip over that last section here. We're going to skip over this and come back to when we talk about independent events. What I do want you to know is that independent events do not equate to disjoint events, right? Those are two different words. Disjoint events are just two events that don't have observations in common. It does not mean that they're independent, and I don't want you to confuse that. We're going to talk about independent events later. And so we're going to skip over this section here. And what we're going to do now is we're going to get to some examples of calculating probabilities. And this is one where we have some data on two categorical variables, right? And so when we have a table that represents a numerical summary of categorical variables, we call it a contingency table, two categorical variables. So the contingency table below contains data regarding whether a person wore a seatbelt or not, given by yes or no, and whether his or her survival was that they survived or died as a result of an auto accident. And so we can see in this table that 412,368 people said that yes, they wore a seatbelt and they also survived, while they were 510 wore a seatbelt but died. 162,527 did not wear a seatbelt and survived, and 1,601 did not wear a seatbelt but died. All right. We want to calculate what probability that an individual wore a seatbelt in the auto accident, and that should be not below, but that should be belt. All right. So the probability that someone wore a seatbelt, all right, let's say That's yes in our thing. So the probability is the number of elements in our sample space that said yes divided by our total number of elements in our sample space. And I'm going to still use S for sample space, but I'm looking for yes here. Well, we look at the total number of yeses is this number plus this number, which gives this total here of 412,878. And the number of elements in my sample space is the grand total, which is 577,006. And if you put that in our calculator, we're going to see, I think I've already done this. Yes, that is approximately, if I round that to 3 decimal places, 0.716. All right. We in part B, we want to know the probability that an individual survived the accident. So the probability that someone survived, we're going to use that probability notation, is the number of people who survived out of the number of people who are in my sample space. So survived, I would add these two, which is already given to us as 574,895, and we divide that by 577,6. And if I put that into my calculator, we're going to see that I have approximately 0.996 people who survived the auto accident. In part C, what is the probability that an individual did not survive, right? Well, if we already know the probability that an individual survived, well, the probability that they did not survive is just a complement, right? And so we could go and do this very similar to what we did in parts A and B. But what I'm going to do is I'm going to do the complement of surviving, because the only other option for surviving is not surviving, right? So surviving and not surviving will be complements of each other. And so this, by a probability rule, a complement rule, this is just 1 minus the probability that someone survived. And so since we already have that that's 0.996, then this just equals 0.004. All right. Alternatively, you can go to your table and look at the total number of people who did not survive. That means they died. And you will see that you can do the 2,111 divided by 577,006. All right. And then the last part of this example, what is the probability that an individual wore his or her seatbelt and survived, right? And so what I will do in this type of example is I will do this intuitively. I'll go to my chart. Survived and wore a seatbelt is this number here. And so based off of what probability tells us, the probability of they wore a seatbelt, that's yes, and survived. Notice we don't have to go back to any of our rules because it's more complicated to do that. I'll just go to my table since I know how many people who survived and wore a seatbelt was 412,368. I'm going to do 412,368 and divide that by my total, 577,006. And I'm going to get that is approximately 0.715. I know I just said that that was our last example, but of course we have two more. What's the probability that someone wore a seatbelt? That means yes. And or, that means to do the union, or they survived the accident, survived. All right, here I'm going to use my probability rules, right? So the probability of a union is the probability of the first event plus the probability of the second event minus the probability of the intersection of those two events. Now, the probability of a yes we found in part A was approximately 0.716. The probability that they survived was approximately 0.996. Of course, if we just use that, we will be over our 1, right? 0.996 plus 0.716 is bigger than 1. This shows you why we have to subtract off the intersection, because the intersection was added twice. We found the intersection in the last example, 0.715. And so if we do that calculation, we're going to get approximately 0.997. Now, alternatively, we could also find this probability by looking at the number of people who had yes and or survived, right? So I can go here and I can see that this, if I add those two together, that's the number of people that survived. I mean, that wore a seatbelt. If I add these two groups together, that's the number of people who survived. Now, if I added those two numbers together and divided by my total, notice I would add that 412,368 twice, right? But I can only add that once because I'm going to get something over my total. And so that or could be that 4112368 plus 510 plus the 162,527. You add that up and divide by your total, and that's actually going to give you the same value that you got, which is that 0.997 approximately. And then last but not least, what is the probability of surviving the accident given that you wore a seatbelt, right? If I wrote that in notation, surviving the accident is survive. Given you wore a seatbelt, that's given yes. Now, I'm going to do this based off of probability rules, right? Probability rules say, okay, give me the probability. This A given B is the probability of A and B. So that's survive and yes, divided by the probability of B. All right, so remember we had probability of A given B equals probability of A and B divided by the probability of B. And so if I do that and write that there, the probability of survived and yes is exactly the same as yes and survive, right? The order doesn't matter. So that's that 0.715. And I divide that by the probability of yes. The probability of yes was found in the beginning, which is 0.716. If I put that in my calculator, I'm going to get that is approximately 0.999, right? So the probability of a person surviving an accident, given that they wore a seatbelt, is 0.999. You're almost guaranteed to survive, all right, even though not everybody does, based off of this data. Now, I did that based off of my probability rules. An alternative way to do this, right, is to look at your table and notice it's given the yeses. This means condition everything on your yeses. That means I'm not going to worry about the people who did not wear a seatbelt. They're not of concern. I'm just out of those people who said yes, right? So if I go back to my table, I'm only concerned with this row of data here. This is what conditional probability means. Given yes. Well, we had a total of 412,870 people who said yes. We want to know the probability that you survive given yes. And so that would be the number that survived and was yes, which was 412,368. And I divided by the total number of yeses. Well, that was that 412,878. You put that in your calculator, again, you're going to get approximately 0.999. Right? And so this is the probability rules, using probability rules or probability in order to help us calculate probabilities. This concludes our video. We'll see you next time.